Welcome back to the deep dive. Today we're doing something a little different. Usually when we talk about the cutting edge of computer science, we're talking about massive data centers or neural networks that mimic the brain or robots doing backflips. But
Today is a little more grounded.
today we are going on a road trip.
Ideally, a road trip with a very specific destination in mind. We aren't just wandering aimlessly here.
Exactly. And I want to set the scene for you. I want you to really visualize this. Imagine you have been dropped into the middle of a country you have never visited before, let's say Romania, specifically the city of Arad.
A lovely city in western Romania, by the way. Beautiful architecture.
I'm sure it is, but here's the catch. You have a flight to catch in Bucharest tomorrow morning. It is non-refundable.
Ah, the classic travel stressor.
Right. You have a map, a physical paper map in your hand, but you have no smartphone, no Google Maps, no Waze, no GPS telling you turn left in 500 feet. It's just you, your eyes, and a desperate desire to get to that airport on time. The question is, how do you decide which road to take?
It sounds like a travel nightmare, honestly. But what you've just described is actually the fundamental question of navigation. And more importantly for our purposes, it's the fundamental question of a huge slice of artificial intelligence.
Right, because today we are diving deep into solving problems by searching. And before you tune out thinking we're going to discuss how to type keywords into a Google search bar, let me stop you. This isn't about keywords.
Or at all.
This is about agency. This is about how an AI figures out how to get from point A to point B when it has absolutely no idea what lies in between.
Precisely. We are looking at the architecture of what we call problem-solving agents. And this represents a massive leap forward from the simpler AI models we've touched on in previous deep dives.
You mean the reflex agent?
Exactly, the reflex agents.
Right.
Think about a reflex agent. It's like a knee-jerk reaction. It sees a stop sign, it brakes, it sees dirt, its programming says suck it up.
It just reacts.
It acts only on what is right in front of its nose at that exact second. It has no memory of the past and no concept of the future. But today we are talking about goal-based agents.
Goal-based. So these are agents that plan. They think ahead.
They plan. They think ahead. They consider future actions. And, crucially, they evaluate the desirability of the outcomes. They don't just react. They simulate. They play out little what-if scenarios in their processing.
I love that distinction. It's the difference between blinking because a fly flew into your eye, which is a reflex, and packing a suitcase because you're going on vacation next week. One just happens. The other requires you to simulate a future that hasn't happened yet.
That is a perfect analogy. And to visualize this, I want us to keep looking at that backdrop we started with, this stylized map of Romania.
Yeah.
It's actually the classic example used in the source text, Russell and Norvig's Artificial Intelligence, to teach this very concept. We have pins in cities like Arad, Sibiu, Fagaras, and a web of roads connecting them.
So, our mission for this deep dive is to unpack this search process. We need to understand how an agent finds a sequence of actions, a specific path, that solves a problem.
And the so what here is huge. I want to emphasize that. This isn't just about maps. This is the foundation of all automated planning. Whether you are a robot arm trying to figure out how to rotate a wrist joint to weld a car door without hitting the chassis.
Which is a surprisingly hard problem.
A very hard problem. Or a logistics program routing thousands of packages, or indeed a GPS finding a route. It is all about navigating what we call a state space.
State space. That sounds like something out of a sci-fi novel, but in this context, it's actually really concrete, isn't it?
It is. It's just the set of all possible situations the agent could find itself in. But before we map that out, we need to clarify one thing about the brain of this agent we're imagining. The source material specifies that for these search problems, we are dealing with atomic representations.
Atomic, meaning radioactive, or just really small.
Atomic in the Greek sense, atomos, indivisible. In this context, an atomic state means the AI sees the world as a singular, opaque snapshot. It doesn't see the internal gears turning.
Okay, so
It just knows, I am an Arad. It doesn't know, I'm an Arad, my gas tank is half full, and it's raining and the radio's on. It just treats the city as a single, indivisible black box, a node on a graph.
got it. So we aren't worrying about the internal variables yet. We're just looking at where am I and where can I go?
Exactly. Later in AI, you get into factored or structured representations, where the agent can see inside the state. But for search, we keep it simple. Discrete states. Observable, known, and deterministic.
Okay, so we're in Arad. We want to be in Bucharest. The clock is ticking. Let's start the car.
Let's formulate the problem.
So sticking with the text example, our agent is in Arad and needs to get to Bucharest. It looks at the map. There are 3 roads out of Era. One goes to Sibiu, one to Timisoara, and one to Zerend.
And here's the catch. The agent knows where those roads lead immediately, but it doesn't know what comes after that next town. It's like driving in heavy fog where you can only see the next signpost.
Which is terrifying. So how do we turn this feeling of, I want to go to the airport, into a math problem a computer can actually solve? The sources list 5 specific ingredients.
We call this the formal definition of a problem. If you can't define these 5 things, you don't have a search problem. You just have, a vague desire.
Okay, hit me with the recipe. Ingredient number 1.
First, you need the initial state. That's the easiest part. That's where we start. In our code, that would look something like in Arad. Simple as that.
Check. We're here. We know where we are.
Second, you need actions. What can the agent actually do? This is the menu of options available in a given state.
Right.
From Arad, the available actions are go to Sibiu, go to Timisoara, or go to Zerend.
Right. It can't go to the moon or teleport to Bucharest. The actions have to be valid for the current state, the rules of the world.
Exactly. And that leads directly to the third ingredient, transition model, sometimes called the result function. This is essentially the physics of our little world.
Yeah.
It predicts the outcome of an action.
So it's the part that says if you're in Arad and you take the go to Zerend action.
The result is that you will be in the state in Zerend.
It sounds incredibly obvious to us humans, but I guess the computer has to be explicitly told that, right? It doesn't know that moving changes your location unless you define it.
It has no common sense.
0 common sense. The transition model effectively defines the graph. It tells you which states are connected to which. And together, the initial state, the actions, and the transition model, these 3 things define the state space. That's every possible place you could ever reach from the start.
Okay, so we have a starting point in this huge, sprawling web of possibilities. But we need to know when to stop driving. Ingredient number 4, the goal test. Are we there yet? The agent needs a specific, computable way to check if the state it's currently considering is the target. In our case, the set of goal states is just in Bucharest. Simple, true, or false.
Simple enough. Are we in Bucharest? Yes. Great. No, keep searching. And finally, the 5th ingredient.
The path cost. This is crucial because usually we don't just want any solution. We don't want to drive to Bucharest via Paris. We want the best solution.
We want the shortest route, or the fastest, or the cheapest, or maybe the most scenic. I don't know.
Right. And we need to quantify that. We assign a numeric cost to each step or path. In the Romania example, the cost is simple. Distance in kilometers. The goal of the agent is to find the path that minimizes the sum of those step costs.
This brings up a really interesting point that the source material touches on, abstraction. Because let's be real, driving from Arad to Bucharest involves a lot more than just being in Arad and then being in Sibiu.
Oh, absolutely. Real driving is. It's a continuous, complex process. You're tuning the steering wheel, pressing the gas, listening to the radio, dodging stray dogs, looking at the scenery.
If the AI had to calculate all of that, every degree of steering wheel rotation, every milliliter of gas burned, every potential dog on the road, just to find a route, it would melt, right?
It would never leave the parking lot. The state space would be, for all practical purposes, infinite. This is why we use abstraction. We strip away the details that don't matter for the problem at hand. We say, for the purpose of finding a route, the scenery doesn't matter, the radio station doesn't matter.
So you're just zooming out?
You're zooming out. You abstract the state down to just location.
But there's a danger there, isn't there? If you abstract too much, you lose touch with reality. You could say the best way is to fly, but you're in a car.
Correct. A valid abstraction means that you can actually take the abstract solution, like drive Arad to Sibiu to Bucharest, and expand it into a detailed real-world solution. It's useful because it simplifies the computation, but it still has to be true. As the saying goes, the map is not the territory, but the map has to accurately represent the connections in the territory.
It's a useful lie.
A useful, truthful simplification.
Okay, so we have our problem formulated. We are in Arad, we want to go to Bucharest, and we're ignoring the radio. Now, before we actually start driving or searching, we need to talk about the test subjects. The source material makes this really important distinction between toy problems and real-world problems.
Yes. In any science, you need a laboratory environment. You need standard, controlled problems that everyone in the field can use to test their new algorithms to see which one is faster or more efficient or, less memory hungry.
The lab rats of AI.
Exactly. The most famous one is probably the vacuum world.
I love the vacuum world. It's so delightfully boring and simple.
It is. You have two squares left and right. You have a vacuum cleaner agent, and there's dirt. The
Right.
state is defined simply by where's the vacuum and where's the dirt.
So let's do the math. Vacuum can be in the left square or the right square. The left square can be dirty or clean. The right square can be dirty or clean. That's 2 times 2. 8 possible states total.
Right. And the actions are go left, go right, and suck. It's a tiny universe, but it allows researchers to prove things about their code. Then, if you want to stress test the system a little more, you step it up to the 8 puzzle.
That's the sliding tile puzzle, right? The little plastic 3 by 3 square grid you get in party bags. Numbers 1 through 8 and 1 missing tile.
That's the one. You slide tiles into the empty space to try and get them in numerical order. It looks so simple, doesn't it?
It looks like a child's toy, something you'd fiddle with on a long car ride.
But the state space, the number of possible arrangements of those tiles, is 9 factorial divided by 2.
Which is?
181,440 reachable states.
Wow, okay, that escalated quickly. From 8 states in the vacuum world to over 180,000, just from a 3 by 3 grid.
And that's just the 8 puzzle. If you go to the 15 puzzle, which is a 4 by 4 board, you're looking at about 1.3 trillion states. The 24 puzzle, the 5 by 5, is around 10 to the 25 states. It shows how quickly a toy problem can become a monster that even our best supercomputers can't solve by brute force.
And then there's the 8 queens problem, another classic.
A classic chess puzzle. You have to place 8 queens on a standard chessboard so that no queen attacks another. That means no 2 queens can share a row, a column, or a diagonal.
The source material mentions something interesting here about incremental versus complete state formulation. What's the difference there? Because it seems like it matters a lot.
It's about how you build the solution, how you even define the search. An incremental formulation means you start with an empty board and you place queens one by one. You place one in the first column, then you find a safe spot for the second one in the second column, and so on.
Okay, that seems logical.
A complete state formulation is totally different. You start with all 8 queens already on the board, maybe all in a line, attacking each other, and your actions are to move a queen within its column to a new square to fix the conflicts.
Ah, so one is building from scratch, the other is fixing a broken configuration.
Precisely. And the formulation you choose changes the size of the search space dramatically. The incremental approach has a much smaller, more manageable search space than the complete state one, which has over 16 million states. So how you frame the question determines how hard it is to answer.
And then, just to really hurt our brains, the text mentions Knuth's 4 problem.
Yes, the legendary Donald Knuth. He posed the question. Starting with the number 4, can you reach any positive integer using only 3 operations? Factorial, square root, and the floor function.
So you could do like square root of 4 is 2, then factorial of 2 is 2, and so on.
And the catch there is the infinite state space. You can keep applying factorials forever and get numbers larger than the number of atoms in the universe. It's a great test for algorithms to see if they can handle, or, more importantly, avoid infinite paths without crashing or getting stuck in a loop forever.
Okay, those are the toys, the controlled experiments. But we promised the listeners real-world applications. Why does this matter outside the lab?
Because the real world is just a very, very complicated graph. Take airline travel.
Oh man, that isn't just location, is it? It's so much more than Arad to Bucharest.
Not at all. A state in an airline reservation system includes your current location, the date, the time, the fare class you've paid for, seat availability on hundreds of flights, connection times, domestic versus international rules. The path cost isn't just distance. It's money, it's time, it's the agony of a 12-hour layover. The state space is enormous.
And what about VLSI layout? That was in the text too. Very large-scale integration.
Designing computer chips. You have millions, sometimes billions, of components, transistors, logic gates, and you need to position them on a slice of silicon to minimize the area used and the total length of the wires connecting them.
Why is wire length so important?
Because if the wires are too long, the electrical signal takes too long to travel from one component to another, and your computer lags. It's basically a massive search problem. Where do I put this gate to solve the layout and make the chip as fast as possible?
It's Tetris with millions of pieces and the fate of computing speed at stake.
Essentially. And let's not forget the really futuristic stuff like protein design. Biologists are trying to find a sequence of amino acids that will fold into a very specific 3D shape that can, say, attach to a virus and disable it. That is a search through the vast space of biological possibilities to find a cure for a disease.
So whether it's finding a flight, building a faster chip, or curing a disease, it all comes down to searching through options. So let's get to the mechanics. How do we actually do it? This brings us to uninformed search, also known, a bit unflatteringly, as blind search.
Which sounds like a terrible way to drive, doesn't it?
Ideally, yes. Why do we call it blind? What's it blind to?
It's blind to the goal. In this category of algorithms, the agent has no clue how close it is to the destination. It can't look at a state and say warm or cold. It can't see the airport tower in the distance. All it can do is generate the next set of possibilities, the successors, and ask, is this the goal? No. Okay, generate the next set.
So it's just trial and error, but systematized trial and error.
Exactly.
Hmm?
And the most basic, most fundamental form is breadth-first search, or BFS.
This is the cautious approach, right? The one that doesn't rush into anything.
Very cautious. Imagine you're at the root of a tree at a rad. BFS checks every single immediate neighbor first. It looks at Zirand, Sibiu, and Timisoara. If none of them are the goal, it then moves to the neighbors of those neighbors. It expands layer by layer, one step at a time.
Like ripples in a pond, expanding outward in a perfect circle.
Yes. And structurally, it uses a FIFO queue. First in, first out. You put the new cities you discover at the back of the line, and you always check the city at the front of the line. This simple structure guarantees that if there is a solution, BFS will find it.
So it's complete. It will always find an answer if one exists.
Yes. And not only that, if all the step costs are equal, like if every road was exactly 100 kilometers, it guarantees it will find the optimal solution. It finds the shallowest goal first.
Sounds perfect. It's safe, it's thorough, it finds the best answer. Why don't we just use BFS for everything and call it a day?
Because of the killer constraint, the one that plagues all of computer science, memory.
The RAM wall.
The RAM wall. The source material has a table figure 3.13 that is essentially a horror story for computer scientists. Let's do the math. Suppose every state has 10 successors. We call that the branching factor, or baubles, or met, 10, and dollars.
Okay, so one choice leads to 10. Those 10 together lead to 100, then 1,000.
Exactly. Now, BFS has to keep all the previous layers in memory to generate the next one. That's how it knows where it's been. So if the solution is just 16 steps away, 16 turns on our road trip. BFS would take about 350 years to run, which is bad enough. But the memory, to keep track of all those nodes, it would require 10 exabytes.
10 exabytes. That's more than all the hard drives currently existing in the world, isn't it?
It's an astronomical number. The book puts it bluntly, and it's a quote worth remembering. Memory requirements are a bigger problem for breadth-first search than execution time. You will run out of RAM long before you die of old age waiting for the answer.
Okay, so BFS is out for any problem of realistic size. It just bloats too fast. What about uniform cost search? How is that different?
Uniform cost is the smarter sibling of BFS. BFS assumes all steps are equal cost. But in our Romania road trip, the drive from Arad to Zirand is 75 kilometers. But to Timisoara, it's 118. They aren't equal.
Right. Just counting one row doesn't tell you the fuel cost or the time.
Exactly. Uniform cost search doesn't care about the number of steps. It cares about the total cost to get there so far. The path cost, which we call AGN dollars, it always expands the node with the lowest path cost first.
So it explores the cheapest path first, not just the shortest in terms of steps.
Correct. And that guarantees it's optimal even when step costs are different. But sadly, it explores in the same way as BFS, kind of like an expanding sphere of cost. So it has the same memory issues, keeps everything in memory, and usually runs out. It can also get stuck in infinite loops. If there are steps with zero cost, it'll just keep taking free steps forever, creating a path of infinite length but zero cost, never getting closer to the goal.
Okay, so if memory is the bottleneck, we need a diet plan. We need an algorithm that doesn't eat so much RAM. Enter depth first search, DFS.
The reckless diver. DFS is the complete opposite of BFS. It doesn't spread out. It picks a path and goes as deep as possible immediately. It goes from Arid to Sibiu, then from Sibiu it picks one option, say Fogars, then from Fogars it picks Bucharest.
That sounds great if it picks the right path. It could find the solution in a few steps.
Big if. A very big if. If it picks the wrong path, it keeps going down into the depths of the search tree until it hits a dead end. Then it has to back up. We call that backtracking, and try the next branch over.
But the memory savings are huge, right? The whole point.
Massive. Absolute game-changing.
Right.
Because it only needs to store the single path that's currently on and the siblings it hasn't tried yet at each step. So we call linear space complexity. To go back to that terrifying depth 16 example, BFS needed 10 exabytes. DFS needs about 156 kilobytes.
Wow. From the entire world's storage capacity down to a single email attachment. That's an incredible difference.
It is. But you pay a steep price. First, DFS is not optimal. It might find a long, winding, terrible path to the goal and stop, completely missing a much shorter path that was just one branch over that it never explored. And worse, it is not complete.
It might not cite an answer at all.
Right. If the state space is infinite, like our Knuth's 4-problem DFS can dive down an infinite rabbit hole and never return, it just gets lost in the infinity, searching forever.
So we have a choice between blowing up our RAM with BFS or getting lost in infinity with DFS. This feels like a bad set of options. Is there a middle ground?
There is. And it's a brilliant, beautiful algorithm called iterative deepening search, or IDS.
This is the one the source calls having your cake and eating it too. So how does it work?
Here's the trick, and it's so clever. You run depth-first search to save memory, but you give it a leash. First you say, run DFS, but don't go deeper than one step. It searches everything at depth 1. If it doesn't find the goal, you throw that away and start over. Okay, now run DFS, but don't go deeper than 2 steps. Then start over. Don't go deeper than 3 steps.
Wait, pause. You start over completely every time. That sounds incredibly wasteful. You're redoing the work of depth 1, then you're redoing the work of depths 1 and 2, then 1, 2, and 3. Aren't you just burning CPU cycles for no reason?
It feels wasteful intuitively. I think everyone has that reaction at first. But structurally, it isn't, and this is the key insight. Remember the tree structure.
Sure. It branches out, getting wider at the bottom.
In a tree with a branching factor of 10, almost all the nodes are at the bottom layer. The number of nodes at depth dollars is vastly larger than the sum of all the nodes in all the layers above it combined.
Oh, right, because it grows exponentially. The base is huge compared to the tip.
Exactly. So regenerating those top few layers over and over again is actually cheap relative to the work of exploring the new deepest layer for the first time. It's like painting a giant pyramid. Repainting the tiny tip is nothing compared to the effort of painting the massive base.
That is a great way to picture it. So the cost of repetition is negligible in the grand scheme of things.
Precisely. And what you get is the best of both worlds. Because it explores layer by layer, it finds the shallowest solution, which means it's optimal like BFS. But because it uses depth-first logic within each iteration, it uses tiny amounts of memory, like DFS. For that reason, it is the preferred uninformed method when you have a large search space and you don't know the depth of the solution.
That is genuinely clever. Now, there's one more strategy here before we move on to smarter searching. Bidirectional search.
Burning the candle at both ends.
Literally, you start one search forward from Arad, and you start a second search simultaneously backward from Bucharest.
And the hope is that they meet somewhere in the middle. The math here is really compelling. If the solution is at a depth dollar, a normal BFS has to explore a tree of size level. A bidirectional search runs 2 searches of depth $2 too. So the total number of nodes is something like $2 times BD2.
Which is way, way smaller, isn't it?
It's exponentially smaller. If B10 and T1016 SAV, it's the difference between 1016, which is 10 quadrillion, and 2 times 188, which is 200 million. It's a game changer, computationally speaking.
There's always a but. What's the catch?
The catch is that searching backwards is hard. If the goal is a specific place like Bucharest, sure, you can just trace the roads out of Bucharest. But what if the goal is more abstract, like checkmate in chess?
Right. There are millions of possible board configurations that are checkmate.
Exactly. Would you have to start a search from all possible checkmate positions simultaneously and search backwards from all of them? It's not feasible. Plus, you have to keep at least one of the search frontiers in memory to check if the other searches run into it, so the memory problem can come roaring back.
Okay, that wraps up uninformed search. We're wandering blindly, bumping into walls or spiraling out in all directions, but we're smart humans. When we drive, we don't just blindly turn left and right. We look at the sign. We have a sense of direction.
We have a hunch. Or, in AI terms, we have a heuristic.
This is segment 4, informed search. This is where things get really, really interesting.
This is the shift from blind to best first searching. We're no longer just generating successors, we're evaluating them. We give the agent a hint. We introduce an evaluation function, which we call 5SX.
And the star of this show is the heuristic function, written as one ANL.
Right. Now is the estimated cost from the current state, new goal. And the word estimated is doing all the work there. It's a guess. It's not a fact. It's the agent looking at the map and saying, I reckon it's about 50 miles that way as the crow flies.
For our road trip, this would be the straight line distance, right? The DSLD from the book.
Exactly. If I'm an Arad, I can take a ruler and draw a straight line on the map to Bucharest. That line might be, say, 366 kilometers. I can't actually drive that line. There are mountains and rivers and other cities in the way, but it gives me a very strong sense of direction. It tells me that moving to Sibiu shortens that line, but moving to Zerend actually makes it longer.
So let's look at the first algorithm that uses this. Greedy best first search.
Greedy search is exactly what it sounds like. It is pathologically greedy. It looks at the options from Arid Sibiu to Misora Zerend, and it asks, which one gets me closest to the goal right now, according to my heuristic? It always expands the node that minimizes no dollar.
It's like seeing the Eiffel Tower in the distance and just walking down whatever street points most directly towards it, regardless of whether that street is actually a dead end a block later.
A perfect analogy. And a lot of the time, that works pretty well. In the Romania map, greedy search quickly finds a path. Arad to Sibiu to Făgăraș to Bucharest. It makes a beeline for the goal.
But I sense another but coming.
But it's not optimal. Because it's greedy, it can be easily fooled. It might take a road that points toward Bucharest but leads into a long, winding mountain pass that adds hours to the trip. For example, in the book's map, to go from Iasi to Făgăraș, greedy search might go through Nimt because it looks closer as the crow flies, but that actually leads you away from the optimal path. It gets stuck.
So greedy is fast but reckless. It gets tricked by false promises. We need something smarter. We need the rock star, the algorithm that, runs the world. A search.
A-star, this is a big one. This is the algorithm that likely routed your commute this morning in your GPS. It combines the best of both worlds. It uses the heuristic, the hunch, but it also pays attention to the path cost, the reality of the journey so far.
So let's break down the formula because it's the heart of everything.
Yeah.
1n equals GIN plus HON. This is critical.
Okay, let's unpack this for everyone. GON is the actual known cost to reach the node. It's the history. It's the gas you have already burned. It's the computer saying, I have driven 140 kilometers to get to this city. It's a hard fact.
And now is the other half?
Right. SNN is the estimated heuristic cost from the node de la to the goal. It's the future. It's the guess.
Yeah.
I think I have about 253 kilometers left to go from here.
And SNN is simply the sum of the past and the future. The fact and the guess.
Right. VFSNES is the estimated total cost of the best solution that passes through this node, $90. A search works by always expanding the node on the frontier that has the lowest event value.
So A doesn't just look at who is closest to the finish line, like greedy search did, and it doesn't just look at who is cheapest to get to so far, like uniform cost search. It looks at the total package, how much have I spent, plus how much do I think I have left.
Precisely. And because of this beautiful, elegant balance between past cost and future estimate, A is both complete and optimal. It will always find the best path, provided the heuristic follows certain rules.
Rules. Okay, so you can't just make up any random number for $1.
No, absolutely not. The heuristic is the key, and it has to be well-behaved. To guarantee optimality, the heuristic must be admissible.
Admissible? That sounds like a legal term. What does it mean in this context?
An admissible heuristic is one that never overestimates the actual cost of the goal. It has to be optimistic.
Optimistic. The algorithm needs to be an optimist.
Think about it. The straight line distance is admissible because the shortest path between 2 points is a straight line. You can never drive a shorter distance than that straight line. So the heuristic says, ideally, the best you could possibly do is 366 kilometers. The reality might be 400 or 500, but it will never be 300. It never promises a shortcut that doesn't exist.
So what happens if I overestimate? Say I'm in a city, the real distance to Bucharest is 400 kilometers, but my heuristic foolishly guesses it's 1,000 kilometers. Why does that break A?
If you overestimate, A might look at that node and say, whoa, that looks like a really expensive path. The total cost is huge. No thanks, I'll go explore this other path over here that looks cheaper. But in reality, that 1,000-kilometer guess was wrong, and it was actually the shortest path. By overestimating, you effectively scare the algorithm away from potentially good paths before it has a chance to verify them. You lose your guarantee of optimality.
Got it. So being optimistic encourages the agent to check things out. It says, hey, this path could be really good. Let's go down a bit and verify.
It's exactly. Being optimistic forces exploration of promising paths. And there's a second, stricter condition called consistency or monotonicity. This is related to the triangle inequality in geometry. It basically says that as you move from one node to its neighbor, the heuristic cost shouldn't drop by more than the step cost. If I drive 10 kilometers closer to the goal, my heuristic value shouldn't drop by, say, 50 kilometers. That would imply I'm magically teleported. Consistent heuristics are always admissible, and they make A run a bit more efficiently.
The text mentions that A is optimally efficient. That sounds like marketing speak. What does it really mean?
It's a bold claim, but it's mathematically proven. It means that for a given heuristic, no other optimal algorithm is guaranteed to expand fewer nodes than A. A is as good as it gets. It doesn't waste time on paths that it can prove are worse than the best one it's found so far.
So we have A, it works, it's optimal, it's efficient. But where does the magic roller come from? I can look at a map and measure a straight line with a ruler. But what if I'm solving a sliding tile puzzle? Or a Rubik's Cube? I can't use a ruler on a Rubik's Cube.
No, you can't.
This is segment 5, engineering heuristics.
This is the art form of AI. How do you invent a good, admissible heuristic for a problem that isn't a map? The most common and powerful trick is called relaxation.
I could use some relaxation right now.
In computer science, relaxation means you relax the rules of the problem. You take the original problem, which is hard, and you remove some of the restrictions on the actions to make it easier. The cost of solving the easier, relaxed version then becomes your heuristic for the real hard version.
Give me an example with the 8 puzzle. That seems like a good one.
Okay, the 8 puzzle is hard because of its main rule. You can only slide a tile into the one adjacent empty square. You have to shuffle things around, which is slow and complicated.
Right.
Relaxation 1. What if we broke the game? What if we played in God mode and said, you can teleport any tile from its current square directly to any other square?
Well, then the solution's easy. If 5 tiles are in the wrong place, it would take 5 moves to teleport them home.
Exactly. That gives us our first heuristic. The misplaced tiles heuristic, let's call it $. We just count how many tiles are not in their correct goal spot. And it's admissible because the real game is definitely harder than teleporting, so $1 never overestimates.
Okay, that makes sense, but it feels a bit crude. Can we get closer to reality without making it too hard to calculate?
Yes, relaxation 2. What if we said you can slide a tile to any adjacent square, even if there's another tile there? You can just slide them over each other like they're ghosts.
Then for each tile, you just count the number of horizontal and vertical steps it is away from its home square.
Precisely. And that's called the Manhattan distance heuristic, or $2.12. It's the sum of the horizontal and vertical distances for all the misplaced tiles.
And the text says 2 out of x is better. Why?
It is. We say that 2h2 dominates $. For any given board state, the Manhattan distance will always be a number greater than or equal to the number of misplaced tiles. Since both are admissible, both are optimistic guesses, the one that is closer to the real cost, the higher number, is better. It gives the A algorithm a more realistic estimate so it can prune more of the search tree.
The stats here in the book are just wild. To solve a typical puzzle at depth 12, uninformed search, like BFS, would explore about 3.6 million nodes.
A nightmare.
A, with the simple $OG heuristic, the misplaced tiles one, explores just 227 nodes.
A massive improvement.
But A, with the better 2R2 heuristic, Manhattan distance, explores only 73 nodes.
From 3.6 million down to 73. That is the power of knowledge. That is the power of a good heuristic. You are converting raw, brute force search into smart, guided guidance.
But we can go even further, right? This is where it gets really clever, pattern databases.
Yes, this is where we stop guessing and start memorizing. Instead of calculating a heuristic on the fly, we pre-calculate the answers to smaller, easier versions of the problem.
How does that work for the 8 puzzle?
Suppose we take the 8 puzzle, but we pretend that only tiles 1, 2, 3, and 4 exist. We treat all the other tiles as if they're part of the blank space. We can actually solve every possible combination of just those 4 tiles and store the true solution costs in a giant lookup table, a database.
So when the AI is playing the full game, it looks at the board, sees where tiles 1, 2, 3, and 4 are, and then it just looks up the exact cost to solve that part of the puzzle.
Yes, and that lookup value becomes the heuristic. It's incredibly accurate because it's the true cost for that subproblem. And if you use disjoint pattern databases, like one database for tiles 1 to 4 and another completely separate one for tiles 5, 8, you could just add their costs together for an even more powerful heuristic.
And a result.
A speed up of a factor of 1 million or more over just using Manhattan distance. You can solve 15 puzzles with their trillions of states in milliseconds. It turns a search problem into a memory lookup problem.
Which brings us back to our old nemesis, memory. This is segment 6, when memory fails.
We keep coming back to this, don't we? A is brilliant, it's optimally efficient, but it has to store every node it generates in memory, in the frontier or the explored set, to avoid loops and redundant paths.
So just like BFS, A will eventually eat all your RAM.
It eats RAM for breakfast. For difficult problems, A will almost always run out of memory long before it runs out of time. The memory usage is its bottleneck.
So do we just buy more RAM? Is that the only solution?
We can't buy enough. For the really hard problems, we need algorithms that are specifically designed to be memory bounded.
Like what? What's the first option?
First, there's a simple combination of ideas we've already seen. IDA, Iterative Deepening A. Remember IDS from the blind search section? It did depth-first searches with a depth limit. ID does the same thing, but instead of a depth limit, it uses an F-cost limit.
So it runs a search, but cuts off any path if its total estimated cost, the F value, gets too high.
Yes. It runs a search with a cost limit of, say, F100. If that fails to find a solution, it throws everything away, increases the limit to the next lowest value it saw, maybe F112, and starts the search all over again. It uses very little memory because it's depth first in nature.
But starting over sounds slow, just like with IDS.
It can be, especially if there are many unique F-cost values. So there are more complex, more elegant solutions like RBFS, which stands for Recursive Best First Search. This one is a little trippy to get your head around. It tries to mimic standard best first search, but using only linear space.
How does it manage that?
It dives down a promising path, but it keeps track of the value of the best alternative path it decided not to take. If the path it's currently on starts to look worse than that saved alternative, it backs up, forgets the subtree it just explored to save memory, and switches to the other path.
But if it forgets the subtree, how does it know not to go back there and waste time?
Before it forgets, it backs up the value of the best leaf node it found in that subtree to the parent node. It leaves a little note saying, hey, I checked down here and the best I found had a total cost of 250. So if all the other paths in the world turn out to be worse than 250, it remembers that it can come back here and try again.
It's like leaving breadcrumbs for itself before it wipes its own memory. That's fascinating.
Exactly. And finally, there is SMA Simplified Memory Bounded A. This is the pragmatist algorithm. It uses all the memory you give it, 1 gigabyte, 10 gigabytes, whatever you have. It acts just like A until the memory is full.
And then what?
When it's full and it needs to add a new promising node, it finds the worst leaf node currently in memory, the one with the highest F cost, and deletes it. It makes room for the new stuff by pruning the least promising old stuff.
That sounds smart.
It is, but it has a weakness. It again backs up the value to the parent so it doesn't completely lose the info. But if the available memory is just too small for the difficulty of the problem, it can get into a state called thrashing, where it deletes a node, then a moment later realizes it needs it, so it regenerates it, then has to delete it again to make room for something else. And the search can grind to a halt, making very little progress.
So there is no free lunch. You pay in time, or you pay in memory.
That is the fundamental trade-off of computer science right there.
So we've traveled from the fog of ARAD, stumbling blindly with BFS and DFS, all the way to the precision of A using clever heuristics and pattern databases.
We've moved from blind wandering to smart navigation. We've seen that intelligence in this context, it isn't some kind of magic. It's the efficient processing of search trees. It's about knowing how to prune the possibilities you don't need to look at.
And using heuristics, using knowledge to guide that search toward the goal.
Precisely. The better your knowledge, the better your heuristic, the less searching you have to do.
Now, before we park the car and end this trip, I want to leave you with one final kind of mind-bending concept the text mentions right at the end. Meta-level learning.
Ah, yes. This is where the AI gets introspective.
We aren't just searching the map anymore, we're searching the search itself.
Think about it. The state space we've been talking about is the map of Romania. But the algorithm itself has a state, what's in its memory, which node is currently expanding, what its F-cost limit is. The meta level is the state space of the problem-solving process itself.
It's watching itself thinking.
And it learns from that. An agent with meta-level learning might notice, hey, every time I explore a subtree that has this particular feature, it ends up being a dead end that wastes a lot of time. So it can learn a new rule, a new heuristic, to avoid those kinds of subtrees in the future.
So the agent isn't just solving the problem.
It is learning how to be a better problem solver. It's optimizing its own search strategy based on its own experience.
That is the step towards true adaptability, isn't it?
It is. It's moving from just following a recipe to becoming a chef who knows when to tweak the recipe because they've seen what works and what doesn't.
Incredible. So the next time you pull up Google Maps or Waze and it finds you a route across a city in half a second.
Remember the massive, massive search tree it just pruned for you. Remember A.
And remember, don't just blindly follow the straight line. Sometimes the best path involves a little detour through Rumniguvelsea. Thanks for listening to The Deep Dive.
Safe travels.